Calculus and geometry are actually really closely related. In fact, one of the first things we do in calculus is learn about the derivative. The derivative, finding the slope of the tangent line of a curve, is a fundamentally geometric idea. So historically, those who have studied mathematics, beginning with early philosophers, have been interested in other geometric ideas. Now it turns out not all of these ideas have been used very frequently, so they're not all necessarily very useful, but they're pretty interesting. And so in this presentation I want to tell you about some of these ideas, just a few of them, and give you a sense of how they might be related to calculus. One very important geometric idea that does play a big role in calculus is the idea of area under a curve. So here I've drawn a picture of a function given by the graph that's shown in red. This represents a function f of x. We have two numbers on the x-axis that I've marked a and b. And we're interested in finding the area under the curve between the values a and b. And so given that function, how do we find the area? Turns out this is a very interesting question that leads to the second big idea of calculus, called integrals. We calculate the area, which I've shown above, shaded in the light purple, as a definite integral from a to b of the function f of x with respect to x. This is something we'll see later in the semester. So, in addition to tangent lines and integrals, mathematicians have done many different things with curves. And given a curve, mathematicians like to look for interesting properties that they might be able to discover or explore. One of the interesting curves that has a lot of interesting geometric ideas is the parabola. So here I've graphed a parabola, y equals x squared, and I've also drawn several vertical lines. So I've got three vertical lines, a purple, an orange, and a red one. So the purple line starts at x equals negative 3/4, negative 0.75, and as soon as it comes down, it hits the parabola and it bounces off. And I do the same thing for the other two lines. One's at x equals a half, that's the orange line, and the third is at x equals 1, that's the red line. The way that the lines bounce off is you take the tangent line at each of the points on the parabola, and if you imagine that those are mirrors, the line comes down, it strikes the mirror, it bounces off, and the angle it bounces off has to match before and after. So how do I do that? Well, the derivative allows me to calculate the slope of the tangent line. And so I can calculate the slope of the tangent line, look at the line that's coming down vertically, compute the angle between those two lines, and then come up with the line that comes off at the same angle in the other direction. Well, if you look at the three lines, there's a remarkable thing. All three lines go through the same point at x equals 0, y equals a quarter. Turns out any vertical line that comes down, if you find where it intersects the parabola, compute the tangent line, and bounce off, just like a light would bounce off of a mirror, every line will go through that same point, which we call the focus. Well, this idea has some really important physical applications. For example, if you ever watch a sporting event, like a football game, you might see on the sidelines these plastic dishes. These are parabolas, and at the focus is a microphone, so that all the sound coming in from a particular direction, which corresponds to those vertical lines, all of those sounds are focused, they're all aimed directly at the microphone so that you can hear an amplified sound. Satellite dishes work the same way, and so does a headlamp on a car, except this time you have the light source at the focus, and all of the light hits the dish of your headlamp and is all shined in a single direction. So parabolas and this concept of these parallel lines coming to a single focus really has some interesting physical applications. So a second example of how geometry and calculus have some interesting connections is through the idea of a pursuit curve. Well, it turns out this was a little too complicated for me to try to put together in my presentation, so I've just linked to a website that has a lot of this explained. Now, just to give you an idea of what's going on, if you imagine a sparrow flying in a straight line, And for visualization purposes, let's just think of that as the y-axis. So the sparrow is just flying up a graph. To the right, we're going to imagine a hawk, and it's trying to catch the sparrow, so it's always flying directly where the sparrow is going. So as the sparrow flies up, the hawk has to keep changing its angle. And as it flies along, it's going to create a curve. And finding out what that curve is, that's the idea of a pursuit curve. Well, the sparrow doesn't have to fly in a straight line. It could follow any curve. So given a curve, if you imagine a sparrow flying along the curve and a hawk at some starting point following the sparrow, the hawk creates a curve. And the question is, well, what's the curve the hawk creates? The idea of pursuit curves is pretty interesting and creates lots of, I think, fun problems. But we'll leave pursuit curves there. If you want to learn more, check out that webpage. So here's an idea that I remember doing in elementary school. Imagine taking a board and hammering a bunch of nails in. We're going to hammer some nails vertically along the left edge, and we're going to hammer some nails horizontally along the bottom edge. So we take those nails, and I tie a piece of yarn to one of the vertical nails. Let's start at the top nail. And I stretch it down to the first nail on the horizontal row, and I tie it. And I do that for the second one down on vertical and the second one over on the horizontal, and I just keep doing that. And so that's what this graph is supposed to represent. Now, even though all of those lines are straight, you can see that there's this natural smooth curve that comes out. The question is, well, what's the curve? Well, the one that I have drawn maybe looks like a fourth of a circle. But if I imagine changing how those horizontal nails are spaced, I might get a different curve. And so the question is, given the positions of the nails on the lines, what curve results? That's what I'm calling a yarn diagram problem. The idea of a subtangent is in some sense playing the yarn game in reverse. Here we start with a curve. On my graph, I've started with a graph y equals 1 over x. Take a point on the curve, compute the tangent line, and that tangent line is going to intersect the x-axis and the y-axis at 2 points. Well, those would be the places you'd hammer your nails in and draw and connect with a piece of yarn. That's the sense that I'm talking about, the inverse yarn problem. The idea of a subtangent has to do with the spacing between the point on the curve and the point on the x-axis. In my figure, I have a point at x equals 3/2 and y equals 2/3. If I calculate the tangent line and follow it until I get to the x-axis, I see that the x-axis has a point at x equals 3. The subtangent corresponds to the space between those 2 points, or the distance between the points. So I take 3 and the original point 3/2, calculate the distance between them, and I get a distance of 3/2. And now I go look for a second point. So if I start at x equals 1, find the tangent line, follow it to the x-axis, I find that it hits at the point 2. The subtangent is the space between 2 and 1, and that's a distance of 1. Here's the third point. My x value is 1/2. Following the tangent line, I go to the point 1. The space between 1/2 and 1 is 1/2. So my third subtangent is 1/2. Well, if I look at my 3 points, the x value on the curve and the subtangent, the distance before I reach the x-axis, I notice that my subtangent is always the same as my x value. Okay, so that's y equals 1 over x. Let's go to another graph. Y equals x squared. On my graph, I have the point 1, 1. I find the tangent line, follow it to the x-axis, and it crosses at the point 1/2. So the subtangent is the distance between 1 and 1/2, and that's 1/2. Here's the second point. At x equals 2, follow the tangent line, it crosses the axis at x equals 1. The subtangent is the space between those, which is 1. Third point, well, I might pick something a little rational. 5/4. Calculate the tangent line. Turns out that tangent line crosses the x-axis at 5/8. The distance between 5/4 and 5/8 is again 5/8. Great. So now I've got my tangent line. Or sorry, I've got my subtangents. If I look for a pattern, I notice that this time my subtangent is always half of my x value. Okay, so that's the idea of a subtangent. Well, I could start maybe looking for patterns. Let's think about the functions x to the n. For different values of n, I get different formulas for my subtangent. When n is 1, that's the line y equals x. Well, the tangent line is the same. Turns out my subtangent is the same as x. When n is -1, that's the example I did earlier, 1 over x. My subtangent was always the same as my x value. N is 2, that's my parabola, y equals x squared. The subtangent turned out to be 1/2 x. If I happen to compute the subtangent for x cubed, I would find out that the subtangent is always 1/3 of my x value. So for power functions, my subtangent turns out to be this convenient little formula, but it always involves the position of the point I was looking at. The idea in the textbook about subtangent was that mathematicians were interested in the question, is there a curve so that the subtangent does not even depend on the point? The subtangent is somehow always the same for all the points. Well, to answer that question, we need to understand better how do you find the subtangent. So let's think through the steps. If I start with a function, y equals f of x, and a point at a, the first thing I need to know is the formula for my tangent line. Well, here's the formula of the tangent line using point-slope form. Y is equal to the value of the function plus the slope of the function times x minus a. Given that tangent line, I need to find out where it crosses the x-axis. Well, that corresponds to y equals 0. So I set y equals 0, and I now solve for x. I first subtract the value of the function, divide by the derivative, then I add the value of a, and here's the value of the x value on the x-axis where the tangent line crosses. The subtangent corresponds to the distance between that x value and the original point, which is represented by the absolute value of the value of the function divided by the slope of the function. So given this formula for the subtangent, I can go back and try to use some formulas. For example, if I take my x to the n functions, my power functions, and I calculate their derivatives, I can plug these formulas into my subtangent and calculate that the subtangent for a power function is simply the absolute value of my value a divided by the absolute value of the number n. This actually recreates the table that I calculated earlier simply through experimentation. If I now consider the exponential functions, I know that their derivatives are the same exponential functions times a number, and that number is the natural log of the base. If I plug these formulas into my subtangent formula, I notice the exponentials cancel, leaving simply 1 divided by the natural log of the base. So now I've found it. Here's a function so that the subtangent actually doesn't depend at all on where I am on the curve. In particular, if I take the special exponential, the natural log is simply 1, so that my subtangent is always the number 1. Well, this is interesting. Anywhere on the curve e to the x, if I calculate this tangent line, follow it to the x-axis, it's always 1 unit away from where I started. So for example, if I take the exponential at 2, follow it back 1 unit, I'm on the x-axis. Let me clarify. Follow the tangent line back 1 unit, I'm on the x-axis. And it doesn't matter where I am. Now, subtangents aren't necessarily very useful for calculations, but they were historically important in motivating the exponential functions. And that's why the textbook used it as an example for why we would be interested in calculating the derivative of the exponential.